Okay, so a couple of quick reminders. You'll have a quiz due tonight by 11:59 p.m. It was at 9:30 this morning. Someone pointed it out to me. I fixed it to be the time it's supposed to be due. Same thing for the Friday quiz. I don't know why I did that. I have a guess, but I don't know why for sure. So they are fixed. MOSFET quiz is due tonight by 11:59. BGT quiz is due Friday by 11:59. So basically the end of the day. Next Wednesday, October 21st, we have exam 2. I will get your updated exam 1 grades up this week. I'm hoping Friday, but just have to enter them in. Not that big a deal for me to do. But I don't know if this applies to anyone because I haven't looked at grades recently. Drop day for all classes, or all 16-week classes, is October 30th. You will know your grade in the class by that point, including exam 2. I recommend talking to me before you drop my class. I always recommend to anyone. If you're going to drop a class, talk to the professor first to make sure you're, thinking it through. But there's no requirement to do so, obviously. It's recommended you talk to the professor if you drop the class. But I like to remind you of that date just in case, either my class or some other class, you don't want the failing grade in. That's the last day to drop without a grade. So your next exam 2 is next Wednesday. I will have that grade posted before that deadline, a bit before that deadline, hopefully by that Friday as well. If there are any questions, let me know. If not, we'll go ahead and start on today's topic, because we're actually going to go back to our MOSFET circuits and kind of look at some multi-stage amplifiers with those. Like we kind of did on Monday with BJTs, but hopefully I won't run long this time. I'll have a better idea on the time because I actually have my phone with me today. So I'll put that in front of me. So, okay. Today, we're talking about multi-stage MOSFET amplifiers. The big reason we do multi-stage amplifiers, and we kind of saw this last time, it's very difficult to get design specifications out of a single transistor. You could get a large gain from a single transistor, but odds are that gain is not going to be very stable. Using multiple transistors allows us to build our amplifiers in a way that's a lot more stable and more and give us a large enough voltage gain to be useful in a lot of cases. With that in mind, let's look at 2 different types of multi-stage amplifiers for MOSFETs. These are the Cascade and the Cascade. The Cascade you will like because it's going to be familiar. The Cascade we're going to have to talk about some stuff with. So we're going to start with pretty traditional MOSFET amplifier circuit. And this will look pretty familiar from last time as well, but you don't have to have the terrible nightmares you did before because it's a lot nicer than a BJT. And so what you see is a pretty traditional common source MOSFET amplifier in series with a source follower, which essentially is going to allow us to provide a small signal voltage gain, but then match the output resistance of our resistor in a way that's more meaningful. This is a bit of a simpler design application than what we did previously, where we had those 4 different transistor circuits, BJT circuits. This is basically a simpler version of what we did Monday. And it's simpler for a couple reasons, as we'll see. And so if you think about this is not ground on here, actually, I apologize. This will become ground for the DC portion, but this is biased in a way that allows us to use a 5-volt source, positive and negative. There's a couple reasons for doing that. Okay, and so this is probably, if you remember from Monday, this is kind of familiar. This is basically that last stage we were doing for that BJT amplifier, where we're just isolating everything. And second to last stage where we had the amplifier, just basically feeding directly into it and not changing the bias state of this resistor. However, keep in mind that there's a big advantage to MOSFETs over BJTs in that we do not have current flow. There's no current flow going off in this direction. It's just the voltage level here. It's just the voltage level here. So we have a little bit of work to do, but we don't have to do too much. And so let's apply 383 kiloohms, 135 kiloohms. RSI is RS1, sorry, 3.9 kiloohms. RD1 is 16.1 kiloohms. CS is just CS. You don't have to worry about it. And this is going to be 8 kiloohms, 4 kiloohms, and 4 kiloohms. We're going to assume this has K equal to 0.5 milliamps per volt squared, and VTN equals 1.2 volts. This one has a K equal to 0.2 milliamps per volt squared, and VTN equals 1.2 volts. So we can go through and solve this. We're also going to make our lives easier. Lambda 1 equals lambda 2 equals 0 inverse volts. We're going to go ahead and say that ID1 equals 0.2 milliamps. And we're going to say that ID2 equals 0.5 milliamps. That makes our life easier because we don't have to solve for the DC parameters. We don't have to go solve this circuit in DC. If you check everything out and want to solve it in DC, it's going to work out for you. But thankfully, we don't have to solve it. It would just not be a fun circuit to solve right now. Okay, so which means we have our DC solution. 1, DC analysis. We have ID1 equals 0.2 milliamps. ID2 equals 0.5 milliamps. We technically do need VGS, but we actually kind of don't, as we'll see in a second. And I'll show you how to do that in a second. So, 2, we want to just find our small signal parameters. And if you don't remember your small signal parameters for MOSFETs off the top of your head, that's okay. GM equals 2K VGS minus VTN. VGSQ minus VTN. And our output resistance RO is 1 over lambda IDQ, which is going to be infinite for us. So we have ID, so we could go through and solve for VGSQ, or we could recognize that IDQ equals K VGSQ minus VTN squared. We have K, we have IDQ, we can get this is a quantity in general, not worry about what its value is. And so that would mean that transconductance, Gm, is equal to 2 times the square root of K I dq. So for our first transistor, Gm1, it's going to equal this 2 times the square root of 0.5 milliamps per volt squared times 0.2 milliamps, which Gm1 is going to equal 0.632 milliamps per volt. Our other one, Gm2, same equation, is just going to equal 2 times the square root of 0.2 times 0.5, which take it as you will. This is milliamps per volt squared. Sorry, milliamps per volt squared, and this is milliamps. That works out to be the exact same answer, 0.632 milliamps per volt. They designed this circuit this way. This is a book problem, page 255 of your book. They designed this problem to give us that answer. That took effort. So credit to the poor person who did that. So from there, we can begin to actually analyze this circuit. So we have our small signal parameters. So let's go ahead and go through and analyze this circuit. And then we'll go ahead and do a couple of steps on this slide, and we'll go to the next one just to do that. So remember, this goes to ground. This becomes a path to ground. We short that. We short this, importantly, and we short this, which means we don't ignore RS1, which would be nice. And then we have our basic circuit. And then we replace these with their small signal equivalent, which basically means we open this circuit up right here. We open this circuit right here. And so we have this. Then we have this. But this is VG2, and this is VS2. VS1 is also VD1, and then this is VG1. So from there, I'm going to take this and redraw this circuit in its small signal equivalent. It's helpful to work a couple of different ways to this. This should be a resistor right here. I apologize. You can work from this side over here. Recognize that VG1's right here, and just say VI, RSI. We can define our input resistance RI. It's just R1 in parallel with R2. And I like to draw this node. You don't have to draw this node, and I call this VG1, which is this right here. And it's an open circuit. And then over here, we can go to this point right here. Put this is VD1, which is going to also just be equal to VG2. We have a path to ground from there, down just through the transistor, because CS gives us a bypass around RS1. We ignore RS1, which is GM1 VGS1, where this is VS1. Then we have a path to ground around through RD. And then when we get to over here, we have VS2 is equal to V out. So we want to go ahead and mark VS2 right here. This becomes VGS2. And it goes straight over to V out. We have a path through RS2 to ground. We have a path through RL to ground. And we have a path going from VS2 to VD2, to ground. And you could actually put this over in parallel with everything if you want to, in the same kind of location. And so I'm going to go ahead and redraw this one more time on our next slide. But I'm not going to go through as much detail as I did it, so I am going to redraw the entire circuit, so don't panic if you haven't copied it down yet. And I'm going to go ahead and flip that around just so you can see how it would look another way. Okay, so this is our simplified circuit. It's not anywhere near as bad as it seems. It's just we're going to have to solve this in steps. And it's helpful to work from V out. So we'll say V out is equal to GM2 VGS2 times RS2 in parallel with R2. We can also write that VGS2 plus V out equals negative GM1 VGS1 times RD1. And what basically that's saying is this voltage right here, you can call this V out 1 if you wanted to, and that is equal to the voltage up across VGS2 in series with V out. That's all that is saying, and that is basically negative GM1 VGS1, that current, times RD1 is equal to this voltage drop across this RD1 right here, and that voltage is equal to that series drop of VGS2 and V out. Which is going to help us out a little bit here again, because then we can say that VGS1 is equal to VI times R1 parallel with R2 over RSI plus R1 parallel with R2. And we can define that as our input resistance, Ri equals R1 parallel with R2. And so we can plug that back into right here. And we can say that VGS2 equals negative GM1 RD1 times Ri over Ri plus RSI times Vi minus V out. Which we now have an equation for VGS2 in terms of VGS2, unfortunately. But we can plug this back into our original equation right here, and we can say that V out is going to equal GM2 times negative GM1 RD1 Ri over Ri plus RSI Vi minus V out times RS2 in parallel with RL. Which is basically just plugging this equation back into here. We can rearrange this and isolate V out if we want to. It's very similar to how we've done this before with other versions of this source follower circuit. We recognize that for a traditional source follower circuit that it's just basically divided by 1 plus all this. So you could actually pull out V out of here, move it to the other side, and we'll get that V out equals negative GM1, GM2, RD1 times RS2 in parallel with RL divided by 1 plus GM2, RS2 in parallel with RL times RI over RSI plus RI times Vn. Which means we can rearrange this again and say that AV is just V out over Vn. So we could just pull out that apart right there and say this equals AV. So for this particular circuit, we can go back and plug everything in. We know that GM1 equals 0.632 milliamps per volt. We know that RD1 equals 16.1 kiloohms. RS2 equals 8 kiloohms. RL equals 4 kiloohms. We know that R1 in parallel with R2 is actually equal to 100 kiloohms. That sounds wrong. No, that's right. 100 equals 100 kiloohms. R1 is 383. R2 equals 135. Kiloohms. Like I said, someone did a lot of work to make this work out this way. So from there, we can plug all these values in and say that this is going to equal negative 0.632 times 0.632 times 16.1 times 8 in parallel with 4 divided by 1 plus 0.632 times 8 in parallel with 4 times 100 kiloohms over 4 kiloohms plus 100 kiloohms. So this RSI equals 4 kiloohms. And so from there, we can just say this is equal to negative 6.14 volts per volt. And again, you aren't getting a huge voltage gain out of this. You're just getting the voltage gain of that original circuit right here, this gain right here. However, you're isolating the input and output resistance of the circuit still, and allowing us to match the impedance of whatever circuit we want to later on. So in this case, we match the impedance of that 4 kilo ohm load. It could have been matching the resistance of that speaker like we did in the problem on Monday. I'll give you all a second to catch up on this. And then we're going to dive into the Cascade circuit. Cascade circuits are a little bit not too bad. They might throw you off just a smidge, and that's okay.